Good evening. Welcome to today's session of the NGIGO Virtual Lecture Series. We are still moving gradually into continuous variable. How we deal with continuous variable. Yesterday we said that continuous variable, before you attempt even trying to apply anything to it, you should actually understand the distribution of that particular variable. And then we said that by virtue of that distribution, if the data is not close together, then you cannot apply parametric analysis to them. So we categorize them into non-parametric and then parametric, where the parametric data are what we call the normally distributed data. Okay, so yesterday what we did was that we started trying to find out how you can get to understand whether your data is parametric or non-parametric. And we also say that for the descriptive statistics, for parametric data, we'll be using means, and then we'll use standard deviations or standard errors to describe them. Whilst in the non-parametric data, we'll rank the data and use the median, the interquartile range, the minimum or the maximum to try and show how the data spread around the center. So we are moving on today, and today is going to be a very short lecture. Of course, it's going to be a very short lecture because you didn't come early. It's already 7 o'clock. So what's going to happen today is that we're trying to use another means of how you can explore your data and be able to understand whether your data is parametric or non-parametric. Yesterday we attempted using what we call the normality tests that are available. We tried using the Agostino, we did the Shapiro work, and then the Komogorov-Smirnov. Then we realized that inherent all of them, you can be getting different results. But we say that in that case, the rule of thumb is that whichever normality test that you used in describing your data, you have to state it, because they will come with different forms. So whilst the data passed for one, they didn't pass for the other. And then we said that whenever you have data that is having a lot of variables in there, as the data become large, it becomes difficult for the normality testers to be able to pick them, because of the fact that the standard error of the mean becomes smaller. Yeah, that's the data now represents the sample data represents the actual true population. So the standard error becomes, that is the inherent errors that are in those type of algorithms that are used in those testers. Right. Another way of doing this is actually do a visual inspection. There are several ways we'll go through with them, but one of the ways that we're going to do today is to do what we call a visual inspection on that particular data. Now, we can do that by using the explore data session of the SPSS or the IBM SPSS, data analysis software. So that's what we're going to try to work on today and see what we can do. So without much, let's just launch IBM. Okay, good. Now the data, some of you I know have the data. I don't think, does everybody have it? Yeah, everybody should have that data now. Right, so we just take the same data that we did yesterday, we just take it into SPSS, and then we try to explore the data and then see, because we know the results that we had yesterday, and we'll see how those data was, because you realize that the skewness was small, but some of the data, almost all the data, the skewness was less than 1, but some of them came out not passing normality. So let's try the same data sets and then see. So that was this data set that we used yesterday. Good. All right. So we actually work with this, that height, weight, age, BMI, right? Good. We don't need to take that much. Waist circumference. Okay, so what we're going to do is that we're going to copy these ones and then put them on a new sheet. We're going to put them on a new sheet, right? So we have them on a new sheet now. So we're going to work to explore this data and find out what they are. In order to make things very easy, one way of taking things into SPSS is I'll just copy this one like this and then paste them transpose, copy it, then go to the SPSS now. Go to SPSS now. I've opened two of them, so I just want to close one. Okay, so go to the variable view and then I'll just paste them there as variables. Good. So now I have the variables names in there. So I'll come to the data section and then I'll copy all the data but without the heading. So I'll copy all the data but without the heading. Yes. So quickly I'll just take them into the SPSS, the data view, and then I'll just paste them. And straight away I have the data in there. Right. So we've gone through these things before, so they are very easy to work. Right. So now we have this and we want to explore this data. So what we do is that we go to analyze. Yeah, we go to descriptive. So as you can see, then when you come to this side, our target is to explore the data. Now, so if you are here and you want to explore the data, you can explore the data in so many ways that you want it to do. But in this particular case, we are interested in exploring the data as one after the other. Now, if you want to session the data and still explore them, sometimes the data altogether may be normal, but if you group them in certain categories, some of the groups may come out to be skewed. Okay, so even when the whole data is normally distributed or parametric, and you are sectioning them into different groups, you should still test the the groups that you are sectioning them to see whether still they pass your normality test. So we don't want to make plenty, so we'll just be taking the age for now. We want to do one before we come around, so we just put the age here. So in the case if we wanted to session it, then whatever we were using to session, we will put them here as a factor, then it will session that. Okay, but for now this is this thing that we want. If you come to this side, you have a lot of statistics that if you want to use, you can click them. We'll come to some of them later, but our interest here is with the plots. So if you come to the plots, there are different types of plots that you can do. Now, one is the stem and leaf, which we are not going to deal with today. Our interest today is on the histogram. The histogram. Then you can test for normality if you want. If you click on this one like this, then normality plots with test will also be done. Right. So we just choose this one for now and then click on okay. Then if you come to the options, it's not anything that you need to bother yourself about. Now you can do only the statistics or only the plots, but we are going to do both. Okay, so the summary statistics will be given and then the plots will also be given. So this is what we're going to get if we click on OK. This is what we're going to get if we exploit the data. This is what we're going to get. Right. So if we explore the data, this is what we're going to get. Okay, so if we come into the results session, you can see that the first is the summary results. So with these summary results, if there were any missing data, you would have seen it. Okay, we have this entry 187 entries in there. So now there's a summary statistics that have been done on the data. So that particular data that we entered, which is the age, this is the mean, that is 48.27, and then that is the standard error of the mean. Okay, good. Now, what is what we call the trim mean? Well, the trim mean means that 5% of the upper extremities of the data has been what cut off, and then the mean has been done. So if there are any outliers, they will be found at those particular places. So those figures will be ignored in computing the mean, right? So we will deal with this 95% confidence interval of the mean. 95% confidence interval of the mean actually is a plus or minus the mean with a 1.96 times the standard error of the mean, right? So we will deal with those parametric analysis as we come to the end and what they mean. So a 95% confidence interval means that the boundaries that you get, it should actually cover about 95% of the population. That's the lower and then the upper boundary. So with this, we are trying to say that even though we are saying the mean age is 48, majority 95% of the population will lie between age of 45.8 to 50.6. Then the other group, 2.5% of them will be lower than the lower boundary, that is the 45.8%, and then the other 2.5% will be higher than the upper group, that is the 50.6%, right? So we'll deal with them one after the other as we go. So this is the median, okay? And again, if the data is parametric, in most cases the median is closer to the mean. Yeah, that is also one of the things that you should get. We will deal with the others. So this is the standard deviation. Yes, but be loud.
Is it 95% confidence interval for me? Is that
for the mean? Yeah. For the mean, yeah.
I thought it was
that is for the mean. So all the summary statistics or the column stats, if you are in GraphPy, Prism, you saw all of these things. All those summary statistics have been done here. So you see minimum, maximum, range, all those interquartile range, all those things have been done here. So the skewness have been calculated, and you see it's not different from what we saw yesterday. Good. And then the ketosis has also been calculated. I'll take my time and explain all of these stats one after the other and what you use them for. But for now, our interest is not even on the summary statistics per se. Our interest is on this. So the normality test has been done, and then you see Komogorov's method says that it is 0.052. That means it has passed normality test. Are you getting it? Yes, but you see the Shapiro work says it has failed normality tests. Hello? Yeah, because the p-value here is this was the same thing we saw yesterday. Yeah, the only thing we are not seeing here is that the Augusto is not in this one.
Are we explaining the Shapiro?
Yeah, we're explaining them.
Because the p-value is giving you the borderline above which there's an unacceptable error. So that if you have said you are going to 95% confident, then you are 5%.
If you are not loud, we can't capture you.
5% to be the error without it. And so the next thing is that if your error then goes below the 5%, then it's acceptable because you have not exceeded the minimum or the threshold which you said is 5%. You will not do more than 5%. And here you are doing below 5%. So
no, you are confusing the p-value threshold of alpha of 0.052. 95% confidence.
So it is out of the 95% confidence that will get the difference of 0.
No. The actual meaning of this normality test is this your data. Simply, if you want to explain them in a literary way, this is your data compared to a normal distribution. Your data compared to a normal distribution. Is it significantly different from a normally distributed data? If it is no, that means it is comparable to a normally distributed data. That means the data is normally distributed. It has passed normality. But if it is significantly different from a normally distributed data, then that means the data is not what? Normally distributed. It is skewed. That means it will fail normality test. Are you getting it? Yes.
I think we are not interpreting this one.
Let me show you why we are even interpreting it well.
Shapiro would have even agreed.
Look at it, it won't, because that what we are doing today is not different from what we did yesterday, but it will be easier for you to get it if I do it here. So let me come up here, then you see the interpretation, because with GraphPad the interpretation are given. Okay, so let's do it here. Column starts. Okay, let's just create the same thing. Let's pick up the same data we are using. Yeah, from Excel. That is age. So we are picking up the age. The one we just run now is the age. I hope you are with me here. Okay, so we send it here. We take it out there, and then we paste it. Okay, so we go to analyze, and then our interest is in column statistics. Then we go to create. So when we come here, our interest is on this one. So Shapiro, Komogorov, let's see which ones. Then just go to, we can choose to, all these ones are the ones that we saw at the established stats other place. You will not get any difference from them. So if you click on OK, so can you see what it is? So see the Shapiro working. The same, virtually the same p-value. Are you getting it? Now, pass normality test, that is alpha equal to 0.5. The correct answer is what? No. And why no? Because the p-value is what? Less than 0.05. Are you getting it now? The p-value is less than what? 0.05. That is significant, so it will not pass normality test. But if you come to, yes, it will not pass normality test. That means the data compared to normality, normal distribution, it is what? Significantly what? Different. So it won't pass normality test. Now you come to the, what do you call it, the Komogorov, you realize the p-value is just the same. Are you getting it? The question, pass normality test, it says what? Yes, because it is not significantly different from what? A normally what? Distributed data. So that is how you interpret the p-value for what do you call it? Normality test, or the three normality tests. Yeah. Yeah, you are comparing your data to a normal distribution. You want to find out, is your data, the data you have gathered, is it normally distributed? So what the test is actually doing is that, so this data that you have, compared to a normal distribution, is there a significant difference between the distribution of this your data and a normal distribution? If it is yes, then it means that your data cannot be said to be what? Normally distributed, because it's significantly different from what? A normally distributed data. But if it is no, then that means the data is comparable to what? A normally distributed data. That means it's a normally, you can assume that it's what? Normally distributed. So in this case, a smaller p-value is rather what you don't want. If your interest is to find out, you want a normally distributed data.
Because it is
Different from a normally distributed data. Are you getting it? That is why when the data side, and I'm saying with the algorithm of looking at a normally distributed data, there is what do you call a standard error of the mean in there. And that is why when the sample size increases, the standard error of the mean becomes what? Smaller. So in that case, it can easily not pass, because you are comparing it with a smaller value. Are you getting it? In the algorithm than what do you call it should be. So in that case, every big data will be seen to be what do you call it? Not pass, because the standard error has become very small. If you look at the data we are looking at, when the summary statistics were done, we realize we have a very small standard error of them. Yeah. Because if you look at the mean that we are having here, so you realize the figures we are getting are virtually the same for the two tests we did with the two what do you call it? Softwares. You get it virtually the same. So this is 0.052. If you go to the other side, this one is 0.001. It's just the decimal places that are changed, which you can change it here too if you want. So the same p value 0.001, and then the other one that we look at the top. Yeah, the other one is also the same.
Below the first one.
Yeah, below the first one, right? Okay. Right. Okay. So let's continue from there. All right. So now the next thing that you want to see is this. So this is a bar, histogram that have been plotted, which represents how the data appears. And if you look at this data, you realize that the mean is 48. So 48 will be somewhere here. Are you getting it? Yeah, visual just this thing because it is large. And you realize that majority of the data will be gathering around the mean. So as you move out of the data, you getting it? This is a very close group. So if you do a visual inspection, in actual fact, this particular data is is normally distributed. If you draw a distance around it, you'll be going this way, and you're getting the sigmoid, virtually the sigmoid thing that we are talking about. Hello? Yes. So this is one distance that you can use to we won't bother with the stem and leaf, we won't bother with the kill plots because it's too mathematical for my liking. I think I chose plenty of things. The next thing we are interested in is here.
No, let me see those.
Take your time. Don't take us to a math school today. We will come back to them later. Today our interest is on these two plots. I should have unchecked them in actual fact. Now, this is also another plot that is a box and whisker that is trying to show you how the data is distributed.
In fact, I prefer this one to those. This is clear.
So you see, this is the data, and this side, this line that you are seeing here is the mean.
That is supposed to be the median, but then anytime it is parametric or normally distributed, the mean and the median coincide.
Yeah.
They become the same value.
So yes, it's here, and then this is showing you how the other data is it is spread around the mean.
So
And yeah, almost evenly spread around the mean.
So
And you can see this side here. These are the the deviations, but you are not seeing any values even lying above them. So if any value fall outside of this one, then that value is becoming an outlier. So depending on the distance that it falls outside these two boundaries, it may be a circle or a star. Now a star means it is far away from the accepted boundary, and then a circle means it's a little closer. But then you have to decide. So one way of what we will come to do, try and then normalize the data. Sometimes it is only 1 point or 2, 3 few points that is actually making the data not normal. So you can deal with those data if you see them. Sometimes it might even be an entry error because the data that is there from your destiny, it cannot be there. So for example, this is age, and you realize that you did your thing among adults, and then as we are working with this, we will see a variable like 8, or a variable like, let's say, 5, which means one of them was 5 years. It could be that whilst you are entering 50, then you entered only 5. Yes. So I'm going to change one of the figures to become 5. Then let's see how this plot will appear.
Is it detectable?
It's detectable. You can use it to detect because it will show you the position of that particular entry, and then you can check and verify if really it is a true figure. Because as Andy Fields will tell you, sometimes the wolf will wear the sheep clothes and enter as if it's a sheep. Hello. Yeah, so sometimes even if it is a true thing, but you want to, if it's just one figure or something, you can choose to take it out. by pruning the data and taking out the outlier? No, because you want the mean to actually represent what majority of the what of the people. So if it is only one or few data that is causing that distortion, don't forget all that we are doing is what? An estimate of. So this age, the mean we want to use to represent is an estimate of the ages of the whole group. So if two people will distort that estimate so that it will not be what? Representative enough of the group, but you take them out and you get an estimate that will represent a lot of the people except the two people, then it's better to take those two people out then do the what do you call it, the estimate that truly reflects the what do you call it, the age of the people that you are telling. So those two people becomes what we call what? Outlier.
Okay, I was asking the medium. Is it the
Come again. Don't be intimidated. Come again.
I'll say the mean. I was. I didn't say the.
No, this is a parametric analysis, so it's the mean that is used.
So the mean is it the line between the two yellow?
Yeah, that is it. This line is the mean.
Okay.
This line.
Yeah, so in that case, the two yellow boxes.
It's representing the distribution of the data, every individual data. So it means that the individual data, this mean is what? 48 point something. So somebody get 49. So all the people here, that means they are about 40 something. So they are coming all the way to like, let's say, almost 60. You are getting it.
So the picture is like this. We are drawing the bell shape with the ends at where we made this line.
Where we made this line.
That would look like a blue. This way. It's a portion
of the.
You see the yellow.
Yeah.
And the line that would have gone through like this. The one line.
Now, how come
this one's
longitudinal line?
Yeah, the two longitudinal. Yeah, this one actually is the minimum and the maximum.
The minimum.
Yeah, this is the minimum and then the maximum. So you see the maximum is lying at 90 something, and then the minimum is lying at what? 80. Yeah.
80.
Yeah. So 18 and then what? 90. Yeah. So this is the minimum and maximum. Are you getting it? Yeah. So what I'm going to do is that I'm going to do the listing that I'm talking about, and then we'll see. Now, it was because in this case my options, I didn't check them well. Let's redo that same analysis. This time around I'm going to check them well. So you see, upon visual inspection you realize the data is fairly normal, but we were saying it was what? Abnormal. So now let's check this one, that the outliers are supposed to be plotted. Okay, then let's come to the plot and ignore a few of the things here. This term and leave thing, let it go somewhere. Normality plots and tests, that's where you see those QQ plots and tests.
I would like to explain.
Yeah, that is how the data distributions are. I don't like them. They look too confusing for me. So I've checked some and I've unchecked some. So now let's see what happens here. This one we've done before. Later he will explain the QQ plot for you. I'm not interested. My interest is here. So now I check the outlier. If there were outliers, you realize that those outliers would have been plotted on this one. Okay, if there were so much of those outliers that are falling out on this, they should have been checked on this one. So what I'm going to do now is that I'm going to do it for the other data so that we will see what will happen. Okay, after that Kweku will take over and then explain the QQ plots whilst I take my leave. I told you today's lecture is going to be very short. Yes, and rest, you support that the lecture is supposed to be short, isn't it?
Yeah,
It is. Okay. All right. So now let's do the same thing. We explore for the other data sets that we have. Okay. So we are now, this one was the what you call age. Now let's do the same thing for the other data sets that we have. Okay. So this is still the age. We are moving down. Our interest is not on the age. We go for the weight. So this is how the weight is also distributed. Okay. Yeah. Can you see? Yeah. This is how the weight is also distributed. And then now, so this box. Hello. Pay attention a little. So you can see that with this box, we are having entry 17 and then what? 54. As going beyond those cards. Hello? Yeah. So these two entries for the weights are being seen to be what? Extreme values. Very upper extreme values. So we can go target this one at what? 54 and then what? 17. So you can go back into your data right now like this and then go to the position what? 17. So the position 17 for weight. Have you seen the figure that is there? 118.
It's too high.
Are you getting it? Compare it to the other group people. You realize they are all 60, 50, 80. Are you getting it? Yes. And then we have 118, which is far higher than the rest. Then we have 105. Then let's go to the 54 and see. Was it 54? That was 54. Yeah. 54 is what? 120. So you realize that apart from this 120 and then the, what do you call it? The 118, the rest of the data are almost virtually around what? 80 to 50, 80 to 50, 80 to 50. Are you getting it? Right. So those two values, extreme values, are outliers.
Okay, so we go back to this thing, what we got the picture.
Yeah.
Box plots.
Yes.
Now, those wastes, the lines, the horizontal lines, we said they are the minimum and the maximum.
Yes.
But you still see that the outlier is above or located above the maximum. It justifies why you should throw them out.
Throw them out.
Because if you have said that the line there is maximum, and let's say it is 100, then it doesn't come out to be the maximum because there's 120 behind that.
Yeah.
But if you have a data, okay,
Yeah.
how do you determine something is maximum?
There's calculation for that.
There's a
And there are
calculation.
3 times the quarter range minus the lower.
It's not just selecting them.
Yeah. Okay.
So we will do that to let's.
Yeah. So when we get to those ones, teacher Kwaku will do that. But for you as an end user, this is what you want to see. This thing comes here, and at the end of the day, you see this box plot. Then you observe it and see how is the data setting up. So if you have the data and you have some things up there like this, and you realize that it will shift the meaning of the data, you can then go and deal with these things.
So you see how relevant it will be for you to see the what we call
The plots.
The plots, not just the plot, but how you will see that the data is parametric before you begin the work.
Yeah.
Do that with the normality test.
Yeah.
Yes.
Because from there, you justify why you should go for the normality test. Then these things can come in and justify. So sometimes your Shapiro or whatever will be saying different things altogether. You look at these diagrams, and there are beautiful things coming out.
So look at this one like this, heights.
Okay.
Hello. Look at heights. So you see, even with the histogram, we are seeing strangers who have decided not to be part of the pack. You see this guy. You see these guys are actually not part of the pack. They have actually separated themselves. That is height. They are actually refused to grow. So they are stunted. You can see them from here. Apart from these guys, you realize the rest of the data would have been what? Would have been distributed nicely.
Now let me add something.
So look at the mean. 1.6 something would have been lying somewhere here. Yeah. The rest would have been around it. Okay. Yeah, but the normal ones are starting somewhere
So,
else.
if you were plotting that curve, tracing the middle part of it to draw that polygon, which will look like a bell shape, and you started from the shorter ones,
Once here,
it means that that one is going to make that place longer.
flat and longer before it will come to this side. So you have a long left tail.
There's few of them which are hard
With
like,
this one, the left to allow you.
Yeah.
yeah, the left tail will be long. So this one will be skewed towards the left, meaning there are outliers at the left.
At the left side.
It also means that bulk of the data is sitting on the right. Exactly.
Hello. Okay. So we'll look at the rest and quickly we'll bring our class session to a close. Let's look at this one for the height and the weight. Let's look at this thing. You realize that with the Shapiro, what do you call Kolmogorov, this particular thing it has still what passed normality. Are you getting it?
Yeah.
But the weight did not pass what normality test. Okay, the weight did not pass, and then the BMI also did not pass. All the rest what pass. When you come to the Shapiro work, none of them what passed.
But we are still saying that you'll be looking at these things and they are failing. You go to the diagrams, get there.
And it's different. You see, so
Yeah.
with the Shapiro work, none of the data is what parametric.
So,
But if you do our own observation, for example, with the age, we ourselves will decide and think the age is okay. There are no outliers.
you want to defend your choice with the diagram.
Yeah.
How do you quote?
The diagram. You just say that you did a box plot for exploration and then outlier and this thing was done
Actually, the
exploited.
histogram, you can have a situation where you can draw the normality curve on it.
Yeah, we'll come in. We'll do that as we go along. We'll do that.
And this one too is talking about the same normality.
This class is a precursor to tomorrow's class.
The real class.
This one is
Be very careful.
Why do you want to do that?
All right. So now you have your normality plots. Hello. Now you have your normality plot. Hello. You just edit the graph. This is the normality plot. So if you have this thing like this, all that you need to do is to just double click on it. If you double click on it, it becomes active, and this is the normality plot. This thing, distribution curve. So you show distribution curve. So if you click on it, which of the distribution curve are you interested in? This is the normal distribution curve. Okay, yeah. So this is exponential and then Poisson. Those ones we are not interested in it now, but the normal one is okay for us. So if you click on that, the normality plots have been done. So have you seen the normality plots? So you realize that it is actually excluding this particular two, what do you call it? Yeah. So this is the normality plots Goku was talking about. So you can see how the data is. So without these two, you could have a very beautiful, what do you call it, normal this thing. So now the question is, these things that are here, who are they? You can actually track them by using the, what do you call it, the box plot. Yeah. So this is it. So you see the 67 is a star. That is, it is very far away from the rest of the what of the data. Whilst the 61 is what? It's a circle. So this is what? This is the height. Let's go and search for 61 and then 67. Let's see those who have refused to grow. 61 and then 67.
Right.
So that is height, right? Okay. So this is 61. That is 1.2. So look at the rest. Look at the rest of the group. Just do a visual inspection of the group. You realize that they are what? 1.5, 1.6, 1.5, 1.6, 1.7, 1.5, 1.6, 1.7. Hello. Yeah.
Which one was the circle? Which one was the star?
Yeah, the circle was this. So the star with the west is yet to come. So that is it. The west is what? 1.1. 1.16. So you realize all the rest are what? 1.6, 1.7, 1.5. Are you getting it? So these ones, they went to what? 1.1, 1. What? 1.2. And that's why they are extreme values. Are you getting it? Hello? Yes. So you can draw your this thing and then observe it. And these observations have been found out to be what? To be better than just doing a normality test. So if you are the type who likes Smirnoff, you can do your Komogoro Smirnoff, all right. Drink it if you want it, but don't forget to inspect the data before you make a decision whether the data is parametric or non-parametric.
So the usual thing is that people don't look at the overall and the screw and all we look at is the three set of drawings. The histogram with the normal curve fitted, the box plot and the KQ plot.
So with this one too, you can see those wide side of the data which were falling here. Those ones are the ones that have been picked up at the box top. Those ones. The KQ plot is there. So we will leave the KQ plot for Kweku to come and teach us what it is tomorrow. He will teach us probability and then Poisson distribution and all those things. God willing, tomorrow. That is if he's going to be here. Are you going to be here? Hello. Yes, it's better to understand data before you get into any analysis. The problem we are having is that people just get up straight away, they start meaning things. Data analysis is not knowing how to use a software. Understanding what you are doing is the most important thing. So exploring the data is the first thing that you do. And then once you understand what data you have, then you can now decide on which statistics you apply to tell which story that you have.
This one you have outlays. But when you look at
the plot, there is an outlier here, is it?
Yes, but when you look at the statistics,
this one.
The box is
the box plot, yeah.
I think it's cast.
Yeah, so because this has not been included in the analysis, this one has been taken out. The outlier has been taken out. So if you take out the outlier, this is what you're going to get. Yeah. So if you look at the plots at the top there, you see that one too. The outlier was excluded in order to get this virtually normally distributed.
So what is your conclusion? It's the outlier.
Yeah, we will come to correcting data, transforming data and all that. There are a lot of tricks that you can use.
The restoration is done first before the main.
Before you decide on how you treat the data.
Identify these things. Out.
Yeah.
So you include the exploration in the write-up.
Yeah, you can. You have to explain how you came into the understanding of your data.
Bring any of these diagrams.
I've seen people that bring their data listing. Yeah, you can choose to, but even some bring even in their but it is actually an exercise that you cannot maintain with certain particular data, like the data sheet that we have seen. Have you seen that every data sheet there is continuous variable? So if you are going to produce, how many graphs are you going to produce? Anytime you session the data into any groups or something, you should still test for normality. So if you are not careful, your normality test alone will be like 200. But you describe how you arrive at whether the data is normal or it is skewed. And there are so many ways of doing it. We will come back to using the numbers to do it again like we were doing it. So after you have gone through all, then now you decide based on the strengths and the weaknesses of the others, decide on how you want to exploit your data. The normality tests that we have seen is accepted if you use that. A lot of people use that alone, but the only thing is that the question is that they are problematic. All right. So on that note, we will end today's session. Thank you for coming. God willing, meet you tomorrow. We'll continue with our data exploration, continuous variable.